thinking about that I want to get excitation energies and transition moments out, it actually makes absolutely no sense trying to calculate this response function from excited states directly. Because then you put in the information which you want to get out of it. That makes no sense. So you have to find another way of getting there. And in order to do that, or in order to motivate what is behind that, I'll ask you to look at this summation here. Let's get it a bit down again. I mean, what do I have here? I have a sum over n. So I have n here, n there, n there. So let's write that once again. Omega, so I have a sum over n. And I can write that as 0 mu alpha n. And then I can write it as h bar omega minus en minus e0 minus to the first n mu b0. And here the complex conjugate. Don't write that out. So I have a quantity here which depends on n times the inverse of a quantity which depends on n and times this one also on n. Now this is sum over n, so there are several of those elements. I might write them in a vector. Stuff them sort of each element in a row vector. So I could get a big row vector here, a lot of elements which all look like this. Different values of n. Similar, I might stuff those in a column vector. Like this. Different elements. And this I could stuff in a matrix, a diagonal matrix, where one of the diagonal elements looks like this. Like this. So this is a diagonal matrix. And whether, if I calculate that and remember what the rules are for matrix times vector and vector times matrix, you can see that this is actually precisely the same, just writing it a different way. Instead of writing it as a sum, I write it as a matrix product. Now, this being a diagonal, I might as well move the -1 out here. So that sum, both sums I can write as a vector times an inverse matrix times another vector where the inverse matrix is diagonal. And I can actually stuff the second part also in there, make the vector longer, and continue the matrix. So I can write the whole thing, both sums together. The only thing I have to do then, I have to switch around. I can move this up here, so I get mu alpha on the left-hand side. And then I have first part where I have these kind of integrals, and then the second part I have the other way around, the integrals. That gives me those then, and then similar I have here a second part somewhere here where the integrals then look like this. And then I'm going to also have sort of down there a part where I have, instead of omega, I have minus h bar omega. and the rest is the same, which is this part. So I can write the whole thing up in a matrix way. And these here, I want to give it that vector, I want to give a name that I call that T, it's a vector T tilde, and yeah, to specify that this was the alpha, let's write like this, of the alpha component of the dipole moment operator. That's all operators. Yeah, I always forget that operator sign. Also here. Now that then is very much the same. Here it's now the beta component of the operator. It's also a vector. And this is now not transposed. This is transposed, that's not transposed. And the whole matrix I want to write up as the thing in the middle, the inverse matrix. I want to write as omega h bar or h bar omega, an S matrix, which here is diagonal, minus an E matrix, which is also diagonal. And the S matrix, that's diagonal, but the upper half is +1, and the lower half is -1. That gives me the minus sign. And that E matrix is En minus E0 in both parts. So I can write then, using that definition, those definitions, where sort of the E matrix, let's write it up here. An element of the E matrix, diagonal E matrix, the n element, would be En minus E0, whereas an element of the S matrix, diagonal, would be either 1 plus or minus 1, dependent whether it's in the upper half and the lower half of the matrix. Good. Doing that, I can write my response function, still with exact states, as T vector tilde mu alpha times this h bar omega S diagonal minus E diagonal inverse times T of mu beta. Like this. It's a vector times an inverse matrix times another vector. So far that's just notation, just writing in a different way to get to a matrix representation. And it's still the exact states. But I mean, we don't know the exact states. We have to work with approximate states, Slater determinants as representations. So what I have to do now is, in these transition moments here, I have to expand those exact states in the kind of approximations we looked at when we talked about correlated wave function methods and so forth, which essentially is a change in basis. I change from the exact state, I express them in the exact states in a basis of approximate Slater determinants and some coefficients, which is just a change of basis. But when I do that, then the matrices are no longer diagonal. So we end up with an expression for the response function which is a vector times an inverse matrix times another vector. And we can express that, and I don't show you the expression for E and S and T for different approximate methods, but we can express those then in whatever approximate method we use. And it's approximate, but still we keep the interpretation of the response function. Meaning the value of the response function is, for example, polarizability. And we still say we can look for poles and transition moments as the residuums at the poles.